Probability with infinite outcomes, geometric probability. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already learned. In our previous lessons, we focused on what we call discrete sample spaces. Now, you might remember that discrete simply means we can clearly identify and count every single possible outcome. Think of something familiar, like the 6 faces of a standard die or the 52 cards in a deck of playing cards. In these cases, the number of outcomes is finite and easy to list. However, as we move into more complex real-world scenarios, we encounter experiments that have an infinite number of possible outcomes. To illustrate this, imagine I asked you to pick a random number between 0 and 1. You might choose 0.5, or perhaps 0.25, or even a more complex decimal like 0.12345, or even a repeating decimal like 0.777, and so on. As you can see, because there are infinitely many real numbers tucked between any 2 points on a number line, it becomes impossible to simply count the outcomes one by one. Since counting is no longer an option, we need a different mathematical tool. This is where we introduce geometric probability. In these instances, instead of counting individual outcomes, we shift our focus to using measures. Specifically, we use physical properties like length, area, or even time to calculate the probability of an event occurring. In the next few slides, we will look at exactly how to apply this to one-dimensional and two-dimensional problems. Length-based probability. Now that we understand that we can't count infinite outcomes, let's look at our first practical application, length-based probability. Think back to the previous slide where I mentioned that we need a new way to measure probability. When our outcomes aren't things we can count, but are instead points on a line segment or even a duration of time, we use the length of those segments to find our answer. To do this, we use a specific formula. The probability of an event E occurring, which we write as P of E, is calculated as the ratio of the length of the favorable region to the total length of the possible region. In other words, it is the length of the favorable region divided by the total length of the region. Let's put this into a real-world context so it makes more sense. Imagine you are waiting for a bus. Suppose a bus arrives at your stop exactly every 15 minutes. If you arrive at the stop at a completely random time, what is the probability that you will have to wait for less than 5 minutes? Let's break this down step by step, just like we will for the area-based problems coming up in the next slide. First, we need to identify the total length. In this scenario, our length is actually time. The total time interval between 2 buses is 15 minutes. This represents the entire range of all possible outcomes, so our total length equals 15. Second, we identify the favorable length. We are specifically interested in the event where your wait time is less than 5 minutes. This 5-minute window is our favorable region, so favorable length equals 5. Third, we apply our formula. We take our favorable length of 5 and divide it by our total length of 15. This gives us P of E equals 5 over 15. Finally, we simplify the result. 5 over 15 simplifies to 1 over 3, which is approximately 0.333. So, you have about a 33.3% chance of waiting less than 5 minutes. Area-based probability. Now that we have mastered how to use lengths for one-dimensional problems, let's step up a dimension. On the previous slide, we looked at time intervals, which are essentially lines. But what happens when our outcomes aren't just points on a line, but points within a two-dimensional shape, like a target or a map? In these cases, we move from length-based probability to area-based probability. The logic remains exactly the same as what we've learned so far. To find the probability of an event E occurring, we simply calculate the ratio of the area of the favorable region to the total area of the possible region. In mathematical terms, the probability of E equals the area of the favorable region divided by the total area of the region. To make this concrete, let's look at a real-world example involving a dartboard. Imagine you have a square dartboard where each side has a length of 10 centimeters. Now, right in the middle, there is a circular bull's with a radius of 3 centimeters. If we assume that a dart hits the square board at a completely random point, we want to find the probability that it lands specifically inside that bullseye. Let's break this down step by step so you can see the process clearly. First, we need to identify our total possible region. Our total region is the entire square board. To find the area of a square, we multiply side times side, so 10 times 10, which gives us a total area of 100 square centimeters. Second, we need to find our favorable area. This is the area of the circular bull's. Using the formula for the area of a circle, which is pi times the radius squared, we take pi times 3 squared. Since 3 squared is 9, our favorable area is 9 pi square centimeters. Third, we apply our probability formula. We take our favorable area, 9 pi, and divide it by our total area, 100. So, the probability of E equals 9 pi over 100. Finally, let's simplify this into a decimal so it's easier to interpret. If we use the approximation of pi as 3.14, then 9 times 3.14 gives us 28.26. When we divide 28.26 by 100, we get a final probability of 0.2826. This means there is roughly a 28% chance of hitting the bull's. As we move to the next slide, we will summarize the key takeaways from both the length and area methods. Key takeaways. First, let's distinguish between continuous and discrete. Up until now, we have mostly worked with discrete sample spaces, where we could simply count the outcomes, like the faces of a die. However, as we saw in our opening slide, geometric probability is specifically used for continuous sample and spaces. These are scenarios where the outcomes are infinite and, quite literally, impossible to count one by one. Second, notice the shift in how we calculate. Because we cannot count outcomes in a continuous space, we move to a measure-based approach. Instead of counting individual items, we use physical measures. As we practiced in our examples with the bus arrival and the dartboard, we use length for one-dimensional problems and area for two-dimensional problems. Third, don't let the new method intimidate you, because the underlying ratio logic remains exactly the same as the classical probability you already know. The core principle is still the probability of an event equals the length or area of the favorable region divided by the total length or area of the entire region. It is still just favorable over total. Finally, remember the range. Even though the method of calculation has changed, the fundamental rules of probability still apply. Your final result will always be a value between 0 and 1, inclusive. In mathematical terms, we say the probability of event E is greater than or equal to 0 and less than or equal to 1. All right, let's take a moment to step back and review the key takeaways from everything we have covered in this lesson. Now, before we wrap up, I want to highlight a few common pitfalls to avoid when you start tackling these problems on your own. Common mistakes. First, let's talk about the temptation to attempt to count. When you are faced with a continuous scenario, like the number interval we discussed in our first slide, you might instinctively try to list out all the possible outcomes. However, remember that in a continuous sample space, you simply cannot list every single decimal between 0 and 1. There are infinitely many. Instead of trying to count, you must always shift your focus to using the length of the interval. Second, be very careful with your units. Whether you are working with the one-dimensional length of a bus interval or the two-dimensional area of a dartboard, you must ensure that both your favorable region and your total region are measured using the same units. For instance, if your total area is in square centimeters, your favorable area must also be in square centimeters before you perform the division. Mixing centimeters with square centimeters will lead to an incorrect ratio. Finally, a common error in area-based probability is confusing perimeter with area. It is easy to get distracted by the boundary of a shape, but remember, the probability depends on the space inside that boundary. When calculating the probability of hitting a target, like the circular bull's we used in our example, always ensure you are calculating the area of the shape, not just the distance around its edge. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. As we've seen throughout this session, moving from discrete counting to geometric measurement requires a shift in mindset, and it is very easy to fall into a few specific traps. Keep these points in mind, and you will be well on your way to mastering geometric probability.